Hey, project day today. We're going to build ourselves a piece of test equipment to test our test equipment. Back in the 80s and 90s, Tektronix had a system called the TM500, and then later on it was upgraded to the TM5000 series of modular test equipment. This is a mainframe, a TM501. You can see it's a 501 because it's 1 bay, but they had a whole stack of these from 1 bay all the way up to 6 bay, and same with the TM5000 series. I believe they had a subset of that as well. So this one here is just the TM501, the 1 bay, because it's lightweight and easy to move around my desk. But I've got a few of these. I think I've got about 4 of these. I've got some a 2 bay, maybe a 3 bay, and I've got a 6 bay, the TM5006. That thing's a big stonker. It's big and heavy, but these are actually really good because you can get all these modules like this one here, a function generator, or you can get a multimeter, or even frequency counters, and a whole heap of more. There's like probably, I'll guess at a rough guess, 100 or so different modules you can get, all different specifications and like different functions. There's audio function generators, there's frequency counters, there's current clamp adapters, so you can get a current clamp and plug that into your oscilloscope and see the current waveform rather than just a voltage waveform that a oscilloscope usually shows. Calibration stuff, oscilloscopes, all sorts of gear. There's heaps of these things. But the problem is, if I buy these secondhand, these mainframes, I need to make sure that they're working correctly before I plug my expensive modules in. Some of these modules aren't so expensive. Some of them are really, really expensive. Some of the calibration modules can be hundreds and hundreds of dollars, even though they're like 20 years old still. So what can happen is if you plug your module in, these things have got capacitors and stuff that can go bad, and also got some transistors in there, some pass transistors, which are often used for the power supply sections of your module. The reason they put the transistors in the power supply rather than in the module is because if they get warm, you want to keep that heat away from the rest of the circuitry in your module, and it reduces cost of the module, and means you don't have to have big heat sinks in the module. You just have it in the power supply, so it means the modules can be more compact. But if those transistors are bad, you plug your module in, you can blow your module, and that's no good if you've got an expensive module. It's no good in any case. And then if you pull your module out and it's blown, you put that into another mainframe to go, oh, what's going on? And then it blows the transistors, and you end up leapfrogging blown transistors and modules. So we've got to figure out a way to test these things so we can just plug a test module in, test it, and then make sure it's working well. And then we know that it's safe to plug in our expensive modules and make up our own little test rigs. So it turns out, after a little bit of searching, the Tektronix actually had a construction note for a TM500 power module tester and utility power supply. And I had a look through this. There'll be links to all of the files and all of the documents and everything down in the description below, including all of my files, because I've done some modifications and some updates and stuff to this design to make it easily built. I like having things where they don't have lots of wires inside, and this is old school where they've got a lot of hand-wired things. So I've updated all that, and I had a look at this and I thought, I could build one of these myself. So I did. So that's what we're going to talk about today. You can see the picture here. This is a 4-bay module here, 1, 2, 3, and 4. I haven't got a 4-bay yet. I want to get one because it's got the high power section, which means you can have higher powered power supplies. You can get power supply modules too. So this is what we're going to build, and I have got some PCBs built thanks to PCBWay. They're the sponsor for this video, so check out their website, and we'll talk a little bit more about some things that they've got going on later on in the video. So first of all, we'll have a look at the schematic, because I wasn't so impressed with some parts of this schematic. So I'll zoom in just a little bit. So that's our schematic, and it's a little bit how you're doing for the way it's laid out. It's a little bit messy, but yeah, there's a few things here and there, like some missing bits and pieces. In the document, this exact document, if you download it from the link below, you'll find that at the end of the document there's some handwritten notes. That's someone else has written those notes, and they've got a few little updates in here, bits and pieces here and there. But I've done even more than that. So there's things like these are like range switches. I've pulled those off out of that schematic and put them onto a separate circuit board. Things like the 5-volt power supply section here, I've added a few more capacitors to bring it in line with the data sheets, the modern data sheets for these regulators, the 7805 standard jelly bean part, and a few other bits and pieces I've cleaned up and made the schematic look a lot better. So let's head over to the computer and I'll show you my design of this. Okay, so here's the main schematic. We've got a few sections of this schematic. This has been redrawn from the Tektronix, and I've massively cleaned it up so it makes a lot more sense. First of all, we've got the positive 15 supply at the top right hand corner here. I've changed the layout of the schematic for the negative 15 in the bottom right hand corner here from the Tektronix version, just so it makes more sense. It's more of a mirror image of the top to the bottom there. So just, you know, so you can see what's going on a bit easier. We've basically got dip chip here in the middle. That's our 741, our op amp and whatever, and that does the voltage regulation through the transistors. And we've got our 15 volt sense, negative 15 here, and the positive 15 volt sense up the top right hand corner, and that's just feedback so that we get 15 volts at the front terminals. That's a separate trace all the way along to the binding post, and we'll see that on the actual front panel PCB itself. So that's you could join it in on this PCB, but then you'd only have 15 volts at that point, not right at the front terminal. Then you see all these little rectangles with the arrows in them. That's all the connectors. So that goes to either the front panel PCB to the range switch PCB, or in the case of a lot of these, the J1s down the left-hand side, and a few of them in through the rest of the schematic. They go to the card edge connector, which plug into the mainframe module. In the center here, we've got the 5 volt power supply. That's mostly the same. We've got a few protection diodes, a reverse bias diode there to protect our regulator if we inject voltage into the 5 volt regulator section. So if you are powering a large capacitor and it then discharges, it'll go around the regulator rather than go through it and blow it up. And I've added a few bits of capacitance here and there to comply with the data sheet for the 7805, which weren't on the original schematic. In the middle on the left here, we've got the connections to the front panel. We've got 2 there and then 2 there. They go to the red LEDs on the front, which determine if our phasing of our transformer windings are correct or not. So if one of those lights up, then it's we've got to swap the wires in the mainframe. If they're both out, they're not illuminated, then our phasing is correct. Here's the range switch schematic. Nothing too special. It's just got 2 connectors and it goes to 2 gangs in each part of the switch. So we've got a 4-gang 6-position switch, and then yeah, it just switches through the ranges as needed as you turn the switch. And the front panel. So here you can see the connector on the right, J2, and then we've got our 2-phase LEDs just there, and we've got 2 switches for selecting different modes. And if we come around here, you see we've got the negative 15 and positive 15. You can see there's 2 traces that come along, and one of them joins in at the end here. That's to indicate that we've got the 2 traces. One is the main power trace, and the other one is that sense trace that terminates right at the terminal there, to make sure that we're getting a good 15 volts right at our terminal. We're not going to deal with voltage drop as our load increases. So if you use this as a power supply or whatever, if you didn't have that sense wire coming right to the end, you're going to have voltage drop because of the copper losses, the resistances in the traces, and as you increase your load, then you're going to have voltage drop increasing as well. So your voltage will drop as you increase your load on that power supply. But having that sense wire come right to the end, that means that that's greatly minimized. Then we've got 2 connections here, one for the scope on the BNC, and then the ground as well. That's between the high and the low terminals, which will be connecting to our multimeter when we do our testing. And finally, 3 LEDs with the appropriate resistors to indicate we've got negative 15, positive 15 and positive 5 volts output. That's just straight to the voltage rails coming out to the front panel. And so over to the 3D software, and we've got the 3D representation of what the thing's going to look like, hopefully. So I've pulled the 3D circuit board and the component layout from my dip trace, the PCB software, back into my 3D software, and that has allowed me to make sure everything fits. So I was able to go back and forth and get all the positions of the plugs and the headers and stuff, and all the binding posts and LEDs all perfectly correct. So I build the size of the circuit board I need. There's the outline there. You can see it in the yellow. Here, I'll make this full size. So that yellow line is the shape of the circuit board. I determine that in my 3D software, put it into my dip trace, and then figure out where the trace is going to go and all that, make sure it's going to fit, and then I bring it back and forth a few times just to make sure everything is going to fit together properly. Get the mechanical design down, so all of these binding posts and the LEDs are all where I need them, and then I can take measurements, you know, say from the corner down to the LED, go horizontal and vertical, and then I replicate that in the circuit board layout software, and then it all fits together as it's shown here, which hopefully it does. So that is what it's going to look like. So also with the front panel there, that's going to be a just a white circuit board, 1mm thick PCB, no trace or anything, just white solder mask with black silkscreen. So all these are black lines, and the text and that, I import that as a DXF back into dip trace and make sure it's all placed correctly, and then I just get the circuit board made, and it comes out basically as you see there, all nice and professional and perfect looking. And all of that culminated in these 4 circuit boards. Thanks to PCBWay for that. Fantastic. Looks real good. We've got our gold plated one because the card edge connector there. Matte black. Looking really nice. I'm actually surprised at how well that came out. It's looking really good. These ones I didn't go for the gold plating because there's no card edge connector. Just standard tin plating. Front panel PCB. Range switch PCB. And there's our front faceplate. 1mm thick, because that's the thickness of the original front faceplate part on the module. And yeah, just white, no traces or anything on there, just white solder mask and black writing. Looking really good. That's going to look really good. Good way to get all your holes and everything perfectly lined up, so your front panel looks super professional. And along with what they sent, along with that stuff, they sent me some stickers too. So I think, seeing as they're a sponsor, they can have pride of place. If you have a electronics oriented business that you think you could offer me some things and you want your sticker front and center, well, speak to me. Hint, hint. They also sent me these things. I'll turn off the lights because these are actually pretty cool. They've got the nice PCBs, and they got assembly services, and they got all sorts of PCBs as well. They're like, you can get flexible PCBs and the Rogers material and aluminium PCBs for LEDs and that sort of stuff. So they've got some really cool stuff. So yeah, check out, link below. These things are actually pretty good. It's just a battery and a switch. I think these LEDs are self color changing LEDs. Nice. Anyway, back to it. Once you got all your PCBs done and you get all your parts from your supplier, you end up with that. Look at that. Beautiful. Nice old school transistors, metal cans, because ain't no school like old school, and they weren't too expensive actually. It's what's originally specified, so we may as well go with that. And yeah, 5-volt regulator sitting there. The power supply up here, we got the positive and negative 15-volt supplies. Once you got it all done, it should look vaguely like this. Look at that. Beautiful. Front panel there. All looking really good. Actually, almost looks professional. So I've made a few little changes here and there. So the orientation of these 2 plugs is swapped around. In the Tektronix version, the scope BNC is in the middle, and the 5-volt output is on the right hand side. I've swapped those because this white one here in the middle is the ground. And if you wanted to put this sort of plug in, this is a standard 19.05mm, or was it 3/4 inch? See, it plugs straight in. And if that 5-volt was over here, you wouldn't be able to put it in because the diagonal distance is too far. So I swapped those, so then if you want 5-volt and ground, straight in. Nice. And on the inside here, obviously I've done all the changes at the front there, so there's no wiring at all. It's all PCBs and plugs. Beautiful. I've spec'd some multi-turn pots. They're Bourne's pots. What are they? They're 3296s. I think they're 30 turn pots. So I can dial in that 15 volts, positive and negative 15 volts real good. I don't have any axial capacitors because nowadays it's all radial. So these large ones, I've just turned them over, put some holes in the circuit board, and just use some cable ties so they're not standing up too tall. And apart from that, it's all pretty much the same. This part of the circuit is all the same. Rotary switch here, which is PCB mount, plugs down into the main board. The front panel PCB here plugs into the main board as well with a 22 pin connector. And yeah, it's all fits together perfectly. So unfortunately, and I apologise, I haven't shown the actual assembly of this. For all the components, it's just the basic, solder parts into the board. Nothing too fancy there, but I was actually figuring out how this all fits as I was putting it together. So it would have been like 5 or 6 hours of video of me putting it in, taking it out, putting it in, taking it out, blah, 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 blah. But to describe how to put it together, you basically want to build this board in its entirety, build this range switch PCB in its entirety, and then you can plug it in. And then this front board, you can solder in the connector and the 3 resistors and the 2 switches, and then you can fit it and slide it into place once you've got all the front binding posts and the LED surrounds in place. And once you slid that in, then you can figure out if it's going to fit, and it should just slide in. What you want to do as well is the LEDs, you want to put those into the circuit board, but don't solder them yet. You've got to make sure that they're the right length, and there's no way you're going to be able to measure it and solder it by hand like without it being fitted and have them exactly lined up. So slide the LEDs into the circuit board, don't solder them, and then slide the whole thing in. Then what you can do is you can get a small screwdriver and just poke the back of them and click them into place. And once this panel here is screwed in with this board is screwed in with the 4 screws, that's all in place. It's all up against the front with the rotary switch. Make sure that this board is eyeball it. Make sure it's as close to 90 degrees to this board as you can, and then that means that that's all going to be lined up. Then you can poke those LEDs through and click them into the little holders, and then solder them into place. I found it helpful as well to these little surrounds on the LEDs. Just put a little dab of super glue behind them, and when you push them in, they glue in place. So when you push the LED from behind, it won't pop out at the front, and that way it's all going to be all nicely locked into place. Then once you got all that sorted, you can go around and just tack the binding post into place. Just you have to solder all the way around. I don't know if you can see there. I've just soldered a blob at the top, a nice fillet little piece at the top there. I didn't bother going all the way around because you don't need to. There's no huge currents going through this thing. So yeah, and then that's pretty much done. As for lining all of these up, what I usually do is I undo the binding post like the thumb screw, and there's holes where you can put a wire. I'll actually get an Allen key, the largest Allen key that will easily slide through, and then I'll slide it through 1, 2, and 3, and that way they're all going to be lined up. And then do the same here, and they're lined up. And this one you can just kind of put one in there. You tighten these back down once the Allen key's through. Tighten that one back down. You can kind of use it as a handle to turn it. I also have some shorting links which I made, but these make it really easy to just plug it in with the Allen keys in, and then you can tighten it up on the back before all this goes in, and that makes sure that they're all perfectly lined up and centered and everything. And that way, everything's going to just plug in perfectly. So you want your wire going to your negative 15 volts. It just plugs in. Beautiful. The high and low go into your multimeter. Just plug it in. Perfect. So that is pretty much constructed. And I've got the front, the top and bottom, not the front, the top and bottom panels to go on, but that will go on later. Before you actually start using this, you also have to set the 15 volts, the positive and negative. The way you do that is you want to turn this around to the PSU mark, number 3, and put the switch here to the PSU, the DC, that's up. This one doesn't matter. And that means you'll be getting 15 volts positive and negative out of these 2 terminals in relation to this one, or in respect to this one here. Put your meter on there, and then you just twiddle the dials. between white and red and white and green. Two little dials till you get 15 volts. Then you're set. Don't have to touch them again. And then that is ready to go into our mainframe to test it, to see if it works. So we'll put the lids on. There's one there. And this one here. Perfect. That is one custom mainframe tester ready to go. So let's get a mainframe out. I'll sit on the desk, change the camera angle, and we'll see how it works. Alright, got it all set ready to go. We've got the meter plugged into the meter terminals, and that comes around to our meter. The BNC here, the blue one, comes around into the oscilloscope. Whoops. And we got these red and black one, which is currently in the positive 15 volts on the ground, to some clips, because we've got our load resistors here. We need a 5 ohm for the 5 volt output, and then a 30 ohm for the 15 volt output. These are just 100 watters I got from eBay for cheap. It specifies in the manual you need like 10 or 15 watt or something, but bigger wattage the better, and these are cheap anyway. So I won't run through the full set of tests because it's going to get boring, but I'll just do a few of the interesting tests. So we'll turn this thing on, and we can see we've got 3 green lights there. That's good. Negative 15, positive 5, and positive 15 all lit up, and the phase 1 and phase 2 are not lit. The 2 red LEDs are not lit, which is good. We don't want that lit, because if one of those is lit, it means one of our phases on the transformer is connected backwards. One of the connections is backwards, and we've got to fix that up. Normally that doesn't make a difference for most modules, but some modules are sensitive to that depending on how they do their power supply, and they won't work if there's a phase backwards. So you can see up here as well, we've got the ripple on our scope. So that's a ripple. We're reading it directly off the transformer, and because there's no load, the ripple isn't very big. And I'm just looking at the paperwork here, if it says how much ripple there should be. It just says, displays the ripple voltage. So and our voltage here is 36 volts, and according to the table it should be 34.3 plus minus 0.5, but that is dependent on the input voltage. So our input voltage might be a bit higher because it's directly off the transformer, then it's going to be a little bit higher. So if you want to be really precise, you can put it on a variac and dial that variac into the center of the voltage range of the tap that you're using. So if you're using like the 100 volt tap or the 110 volt tap, you can dial it in and measure it more precisely, but it doesn't matter for what we're doing here. So next we can hook up the 30 ohm load. So I'll get these wires, and we'll hook these up, and what we'll see is we'll see the ripple go up because we're loading up the transformer, and we'll see the voltage here go down. So at the moment we're at 36 volts, and we're at 160 millivolts peak to peak, and yeah, the ripple's gone way up. The ripple will be will go up less if you've got good strong capacitors, and if they're worn out, you're going to get more ripple. So I'm going to change that scale there. So at the moment we've got 1.74 volts peak to peak of ripple, and we're at 31.5 volts. I'll have a look here to see if it says what the ripple should be. It just says increase in the ripple. Refer to table 2. So table 2, 28 volts, we're at 31 volts, plus it looks like the ripple should be less than 2.6 volts. So that's 1.76, so it looks like it might be alright. And then if we throw this to the DC, no sorry, flick it to the AC, we'll see that increase again, and that decrease. So at 25 volts now, and I've got to drop this down, and now we're at 8 volts peak to peak. And it says here the typical value is 22 to 28 volts, so that's good, 25 volts, and the ripple is between 6 and 11 volts, so we've got 8 volts, so that's fine. So for that test, it looks like it passes. So I'm going to disconnect the resistor before it overheats and melts into my desk. Ah, it's only warm. Now the other test we can do, and I have to set this up right, is test a 12 volt DC supply. So that's going to we're going to plug into our 5 volt output here because that uses the 12 volt windings and whatnot. So we want to go back to position 1, AC, and position B, and then we'll be showing the ripple. Now I've got to turn that back down again. So there's our ripple. I'll just adjust the leveling and stuff. It's a little bit jumpy, but that's alright. So if I plug that into the 5 volt output, now we're getting a 13.2 volts, which is fine. And oh well, what's it saying? Table 3, 12.8 plus minus 0.5, but our voltages are a bit higher, so that's fine. And if I connect the load, the ripple should increase and the voltage should decrease because we've loaded up that winding on the transformer. And our ripple is now just under 1 volt, 950 millivolts. So that is looking okay because it says we should be getting 9.3 volts, but we're higher, of course, and the ripple should be under 1.8 volts, and we're getting just under 1 volt. So that is good. Our 5 volt side of things, 12 volt winding, is good. So that's thumbs up. Our tester is working. So I can go along and test all my other units I got around the place and make sure they're all working good too. So I hope you find that interesting and informative. I'll have all the design files for this thing in the description down below, and you can download the Gerbers and the bill of materials and everything, and you'll be able to make one of these yourself, and it should just work. So yeah, that's it for this video. So don't forget, check out PCBWay, the sponsor of this video. They do make some good stuff, and we'll see you in the next one.